Alright, are we live? Hello, hello, hello. Alright, I think we're here. And what we're going to look to do is solve another problem. So hello and welcome. Boy, just want to solve a problem, just do something before I do anything else. Oh, I've been thinking about so many different things. Yeah. So, anyway, yeah, I want to solve a problem. I don't know, I feel like I'm wasting time, doing all kinds of random things in life and having different thoughts and all that, and I feel like I should just focus for a minute, solve a problem, be somewhat productive, right? Somewhat productive. Alright, here we go. Minimum height trees. Let's do this. Let's do this thing. A tree is an undirected graph in which any two vertices are connected by exactly one path. A tree is an undirected graph in which any two vertices are connected by exactly one path. True, there's no cycles. In other words, any connected graph without simple cycles is a tree. Heck yeah, there you go. Given a tree of n nodes labeled 0 to n-1, an array of n-1 edges where edges of I equals a sub I, b sub I indicates that there is an undirected edge between the two nodes a sub I and b sub I in the tree. You can choose any node of the tree as the root. When you select a node x as the root, undirected, right? Yeah, undirected matters. Directed versus undirected is a difference, significant difference. You can choose any node of the tree as the root. When you select a node x as the root, the result tree has height h among all possible rooted trees. Those with the minimum height, a min h, are called minimum height trees. Oh, interesting. Okay. Oh, that's kind of neat. Turn a list of all MHT's root labels. Oh, you can return the answer in any order. The height of a rooted tree. Oh, okay, the roots. Alright, the height of a rooted tree is the number of edges on the longest downward path between the root and a leaf. Huh. Interesting. So n equals 4, edges 1, 0, 1, 2, 1, 3, 0, 1, 2, 3, 1, 0, 2, 3, 2. So each node has a root, and you get the height of the tree. I guess this is as simple as like, basically, you can write a routine that just gives you the height of the tree, and simple depth first search gets you the height of the tree, and subroutine, and then you just execute that on every root node to get you height. And I guess what you would do is you'd say, you'd just have a vector, a return vector, and you say if, and you keep track of the minimum height you're looking at, and if it's minimum height, right, not maximum height, minimum height, yeah. So if the height you're looking at is larger than the minimum height, then you just don't consider it. If you find a height that's smaller, then you start a new vector, or empty your vector, and add that minimum smaller height to that vector, and then just at the end of it return what's in that array. Yeah, do it that way. Really simple, I think. Really simple routine. I think we just need a routine that works nicely for the depth first search and finding the height. The child set. We just have to set up the child set correctly. I think it's a relatively easy question. I don't think there's really much to consider with regard to like how efficient this is, because these are like arbitrary trees. It's kind of hard to know what the height, like if there's a more efficient way other than just like going through the whole tree to find out the depth. So yeah, I think it's just a depth first search from every node, and that's it. And do as described. Yeah, I think that's it. What's this A sub I, B sub I? What is that? Edges, yeah, I got that. Okay. They're distinct. Input's guaranteed to be a tree, and there'll be no repeat edges. Neat. Alright, I mean, this is like pretty straightforward, I think. I think it's pretty straightforward. We'll try to do this quickly if we can. Try to do this quickly. So to handle the child set, we're gonna do we're gonna go ahead and do 2 vectors. Yeah, edges. How do I want to do this? I'm basically going to copy the edge set twice. So I have all the edges from A to B and all the edges from B to all the children at any particular node. Yeah, we'll just something like this. Children, we'll just say children. And we're going to say children edges dot size, oh not edges, n really, oh yeah, and empty vector, and children of A, push back B, children of B, push back A, and then now we say auto DFS, int, we basically want, yeah, I mean there's a few ways we could do this, but we'll say auto F to be recursive. We want the parent node, and then it's kind of all we need. Now we have like a state that we're going to be using. You kind of just have to set up the initial state, I guess. Which you could, there's a few ways to do this. Yeah, you could do it this way too. Kind of, you could do it this way. What is state a keyword in C++? Because I've noticed it actually ends up being highlighted whenever I try to use it. I don't know why that is. I don't think state's a keyword. No. It's really weird. Why would this be highlighted, I don't get it. But anyway, a few things, this state struct, which is going to be, there's a set, unordered set of visited, or you could do it this way, vector or booleans visited. Actually, we have vector already, so we visited what we visited already. And then we have the parent we're going to give at each step, and then we have the return value. We're going to just say height, h, or depth, however you want to call it. And you basically set the initial state and then modify that as you go. And I think it is that simple. It's really just base if and then there's a current node. So if current node there's no children, you just return, there is no base case, you just return 0, right? So there is no base case actually. Oh, yeah. Don't revisit visited nodes. So if s dot visited of current, if you've already visited, and return 0, I guess. Just thinking, what it's more like something you return. You really want to do it this way, actually. Just thinking. Hold on. You wouldn't modify the depth, basically. If there are no children, then the depth is the same. Just return the depth. That's not really correct. I'm sorry. Let me think here. You actually don't even need to. Yeah, hold on. I'm just thinking here. How do we do this? This is really part of the state. Like, that's the thing. It's like some of these are part of the state, some of these things aren't. We'll do it this way. Like, it's a little confusing. Like, some of this stuff you can, you put right in. Like, basically all of this could be put in to the state. Like, it doesn't have to be, you can do all of these things in the state and then do it this way. That's really how it should be done, I think. Makes the most sense. But anyway, so if you've already visited this current value, then I don't know what you return. You should do it this way, I think, if you haven't visited this. Right, set it to true. And you just say for each child in, it would be children vector of s.current. If c is not equal to s.parent, and s.visited of c, and you haven't visited it yet, then you're going to you're going to modify the state and call f with c, and you're going to say a couple things. Int you're going to do a few things. Modify the state and call f again, and you really don't have to return anything. Like, it's really not, because everything's excuse me, everything's going to be modified here anyway. So what you do is you say, okay, first things first you take the depth and you add 1, and here you return the depth to whatever it was. There's a bunch of different things. So really you could just have a state, nah, I shouldn't do it that way. It's just A, B, C, D. A is the depth, B is or A is ret. We don't need to modify ret. Depth we want, so D equals depth. We want the parent, D equals parent. I want to return that to what it was. And then C, our current, we'll call it, is equal to s.current. Could just do it this way. Parent depth. What you're going to do is modify each of these things. So s.parent is set to, for that child, the parent becomes the child, and s.current that gets updated to, or excuse me, s.current becomes the parent, the new parent, and s.current gets set to C. You call f of f with s up to a new state, and then we reset the depth back to depth, parent back to the real parent, and then current back to the real current value. And what you say is depth plus equals 1, and and ret is going to be equal to, now this is, so ret is going to be equal to standard min of ret and s depth. Now the depth, we're trying to maximize the depth of ret and depth plus 1, or s dot depth. Yeah. Do it this way. Okay. That's pretty much it. Now what we're going to do is call this DFS from each node. And we're going to say DFS, the state S. And we're going to set each of these things to, so S visited is going to be vector booleans of size n, all false. S.ret is going to be equal to int max. No, actually ret is going to be 0 initially. Depth is going to start off at 0. Parent is going to be I. Current is going to be I. Parent is -1. It could be -1 initially. There's no parent initially. And now you call these things and you get the depth. So we say int min depth equals int max. And we say vector int ret or result, doesn't really matter. Now we set the state to these things, and now we DFS. And now we say this is taking me a lot longer than I thought it would. Okay, we say if min depth is greater than s dot ret, right? If the minimum depth is greater than the return value, then I want to set the min depth to, or less than, excuse me. It's the other way around. It's, well, I think, yeah, if the value that we just looked at is smaller than the minimum depth, then we set that value end, we set res to standard vector int, and we push back, and in any case we're gonna push back oh wait, if it's smaller, then we push back hold on. If it's equal, if s.ret is equal to the min depth, right, a little confusing, but okay. It's actually I is what we want to push back, right? So something like this. See if it compiles. Doesn't, of course. I don't know why I missed int here. Ret s.ret from the state. Where is that? Did I miss something? A36. Where's that? Oh yeah, this one. I missed something. DFS, SDFS. And oh, I made a lot of these, huh? What did I do wrong? Deduce return type cannot be used before it is defined. Oh, it doesn't return anything. Wow, there's a lot. A lot of things here. Oh, it works. Okay, not only does it compile, but it seems to be, might be correct. Let's try a few different cases. There were a couple things I wanted to look at before I started testing this. Explain that briefly in a moment. Oops, whoa. Whoa. How long did this take? Almost 25 minutes. Alright. I think we can go for it. Yeah, let's go for it, see what happens. Time limit exceeded. No, really? That's upsetting. What? Serious? No kidding. That's upsetting. What? Really? Really? That's annoying. There are a few things to say here. A couple things. So first things first, I think I got this right. At least this part. I didn't really think about that, how big this was going to be. 2 times 10 to the 4th. Yeah, so this is kind of expensive to do it this way. That's my mistake. I should have thought about that some more. I did. Okay, so I guess the first thing is that I was actually correct in terms of like programming this. There was like one more thing I wanted to check, which was just make sure that this is set up correctly. That if the return value matches the minimum depth, then you just keep pushing back values. However, if the new return value is a smaller depth, then you want to update and start pushing those back. But the thing that's interesting is how do you know which node is going to have? Well, basically, I guess I want to say something like every node you could figure out the path between every node, like there are no cycles. There's only one path between each node. Yeah. So you can figure out the distance from 0 to every other node, and 1 to every other node, and 2 to every other node, and 3 to every other node, something like that. And basically, for each node, you want to know what the longest path is, or the shortest. Yeah, you want to know. You basically want to minimize all of the paths. So this is a pretty interesting question. Caught me off guard. I definitely didn't get the right answer initially. Ouch. Oof. Oof. Yeah. Yeah. Well. What is an algorithm to find? Yeah, that's just a good question. This is definitely a good question, challenging question. Not just a simple depth first search, that won't do it. Because basically each node has a maximum path, and if you find all of the paths, all of the path from 0 to every other node, and while you're doing that, you discover that the path from 1 to every other node is smaller, is better. So you basically get rid of 0. I mean, you can kind of easily eliminate the leaf nodes if they've only got one edge. But that's not really enough, right? I mean, you get rid of half the nodes that way. Right, because if they only have one edge, then, obviously they're not going to be the optimal unless unless all the nodes are leaf nodes. No, they can't be. No, right. One edge doesn't work unless you're dealing with only two nodes. So the leaf nodes basically couldn't be. So that should get rid of about half of the nodes. And now you have your options between 0, 1, 2, and 5. You have between 3 and 4, right? And actually ends up being 3 and 4. But that only takes care of half of the nodes, right? You need something more efficient than that. I guess what you could do is you could say, well, realistically, the best possible nodes would probably be the nodes that have the most connections, right? Those would probably be the ones that would sort of those would probably be the ones, excuse me, that have yeah, those nodes would probably have the smallest depth. Let's consider the node with the largest number of connections to it, and make that the root, right? Let's think about that for a moment. Then for all of those nodes that pass through that node, right? If this is not the root, then all of the paths through that node would get an extra value for the depth if you don't make that so if you don't make that the root, then all of the paths that flow through all of the other roots will get an extra value for the depth. So basically all of the other candidates all the other roots so for that node, all of the nodes that flow through it, if that node's not selected as the root, then all those other nodes, the paths to these other values, since there's no cycles, there's no other way to get through, all those depths would be increased by 1 to all the nodes that it goes through, right? So there's basically some other, and actually it's every path for every node has, at some point, it's going to have to pass through this node to reach the other nodes. So to reach the nodes that it's connected to, I guess. And so the path would increase for all of them. I don't know, it seems like a heuristic. It doesn't seem obvious or clear why that would be the way to do it. Excuse me. Huh. Yeah, I mean, because what I'm thinking is, well, clearly all the leaves, you have to try all the leaves first. And unless you have exactly 2 nodes and 1 edge between them, all the leaves would be eliminated, right? They wouldn't have, and actually I think everything's connected too, right? To make it a tree, everything has to be connected. So there are n nodes and n-1 edges. And so that would imply that if you have more than 2 nodes, then you must have 1 edge with more than, you must have at least, actually every leaf node will have if you have n nodes, n-1 edges, tree, there are no cycles, then all the leaf nodes, in other words, they only have 1 connected edge to them, necessarily the path can't be the minimum. The depth, if you were to root that node, can't be the minimum depth for the tree, because exactly the node that it's connected to every path, yeah, because every path through that a leaf node to every other node, you can just root yourself at exactly the node that the one node that this leaf connects to, and now all the paths to that node are one less. They're actually exactly all the same paths, except one less, and yeah, and unless there's only two nodes and that's the only node that you're connecting to in the first place, that means that would be a better route. So the leaf nodes cannot be. Now, what about nodes with two? In other words, they're not leaf nodes, but they're internal nodes that only have two connections, right? So they've only got two incident edges. They've got basically they connect to a leaf node, or they don't necessarily connect to a leaf node, but they connect to one node, and then they connect to some other node. There's some sort of a connector. I'm thinking like the next level, right? Like all the things that the leaf nodes are connected to. Let's think about those for a moment. Would those make a good route? Well, I think the same argument applies, or let's just do one level up. So nodes that aren't internal, they're internal nodes, but they're not leaf nodes, and they're connected to leaf nodes, right? That's sort of the next level. Those you can make the same argument because internal nodes, they're connected to leaf nodes, and they only have two connections to them, right? There's one to the leaf node and one to something else. They have the same argument for the leaf node. You can make the one that's not the leaf node, that could be the root, sort of the node that's not the leaf node, the other one. You can make that the root, and again, all the paths would be better there. And now the thing about that is you have to be careful in terms of how many it may not necessarily be better, right? Because you could have a situation where that node, every node is a leaf node connecting to it, and so both of these nodes really are sort of equivalent in terms of possible routes. Let me think. Yeah, because let's call it sort of A and B. A being has a single leaf and then is connected to something else, and then B is the other thing that A is connected to, and B is just connected to nothing but leaf nodes. Actually, in those cases, either A or B would make a fine route because you would have a path of two. The depth of that tree is always going to be two, no matter which one you pick, A or B. Interesting question. This is a really interesting question. I want to say something like this, like every node has a minimum path or maximum path, we'll call it. So every node has like sort of a furthest node away from it. And I want to say what you can do is you can do that sort of recursively through the tree where if you just pick any particular route, you say, okay, the max path from this route is going to be, for all of its children, whatever their maximum paths are to any other node, it's going to be the maximum of all of those plus one, right? And then, and similarly for each child, you do the same thing. It's going to be, but now you have, now the thing that's tricky about that is there may be, so I don't quite, I'm not sure about that, right? Because there's a kind of like certain directionality that's assumed. It's like you really want the maximum path between every node and every other node, something like that. So it doesn't include the parent node. It's the maximum path to every other node, but not including the parent node, which is a little weird because I don't know, like let's say you pick a leaf node as the root, and there's like a maximum path that you get, and then the first child is obviously the maximum path is a little bit smaller, but maybe I don't know, man. That's it's a little weird. It's like hard for me to think about how exactly to do this. I'm just gonna say I don't know the answer to this. Doing this efficiently, but I want to say something like you can find, because I'm trying to use a different algorithm than just the depth algorithm, because that's kind of what the depth algorithm is. It's just, you know, take the depth of each of these other nodes as if they were the roots, and then just add one. But the problem with that is that if you take the depth of one of these root nodes or one of these nodes, you don't consider, I guess, connecting it to the other nodes. Huh. Yeah, you can find the maximum path from the root node to any other node, but that doesn't necessarily help you with just the maximum paths for every node to every other node. Like that's kind of what we're looking for. We don't. It's a tricky thing. This is a tricky thing. Um. I almost want to do like a breadth first search from every node at the same time, like do a level order search, something like that, where you have every node in the queue, and then you have every child node in the queue, you know, and you give each of those, right? So there's like sort of level 0 for every node, and then every node that you can reach gets a mark of 1. And I guess I'm not sure though. Like, how does that help? Like, what is? I don't know. I don't know, man. I gotta think about it. Shoot. Excuse me. Excuse me. So I'm thinking about this problem quite a bit. A lot of thinking. Oh, I forgot the problem even was. What was the question again? Oh yeah, right. The minimum path to any particular node from a particular node. Well, I guess you can. I guess you could do something like from the root node. You have, let's say, recursively find the path, the longest path to any particular node for each child, right? From the root node to that child, right? Or I guess recursively, sort of, not including this parent, right? So this child to every other node that it can reach, not going through this parent. Right? Let's suppose for a moment that we did that recursively. Then you would say, okay, but for all of the nodes, so you find that number for all of the children, right? Setting this to be the root node. Now, you could take that node's path and you could now connect all of these children to each other through the root node, and there would be sort of this round robin, I guess. So because you have to go through the root node, right? So it would be, you would update each child with the path to every other child. You go to every other child you've already found. But really you'd add two, right? You'd add one jump to go through the root node and two jumps to go through the root node. I don't know if you could do that. Like, I don't know. I don't know if that's recursively, if that works. Like, that's what I'm kind of getting stuck on. I'm not sure if there's like how to do this. I'm not sure if this is as simple as just writing a routine that basically any particular root node you select that kind of partitions the tree. If you partitions the tree into different sections, into sort of connected components, and you can find sort of the minimum paths amongst all the nodes in that connected component, and then all of those minimum paths, or maximum paths rather, you can then compare them to each other through the root node. Does that work algorithmically? Does that make sense? I'm basically trying to find an efficient algorithm to find out the maximum path for any particular node to any other node, right? The furthest, how far away is the furthest node? Let's pick a random root node. We'll say all the calculate. Let's say we somehow we calculate all the maximum paths to all the nodes from all the nodes for each of these. Let's just call them subgraphs. Really, they're subtrees. So each of these subtrees, let's say we have the answer for each of these subtrees. That for each of these subtrees, we know the maximum path for all the nodes to all the other nodes within that graph, right? Within that subcomponent. Yeah, obviously there are a whole bunch of nodes that won't be included there, but let's just say we know that. What we do know is that every path in that subgraph, all the paths to all the nodes, in order to reach any of the other nodes and any of the other subgraphs, let's say, they have to pass through that root node that we're describing. And I want to say something like, let's just consider two different subgraphs, right? Let's just do it that way. Start with the simplest case first. Two different subgraphs, one node that connects these two. And let's say we found the answer for the left set of nodes. It's like we're looking for like a kind of a divide and conquer algorithm of some kind, right? Let's say we found the answer for the left subtree, and then we found the answer for the right subtree. When we connect these two, I guess there's a set of nodes. Let's say like we answered the whole question for the left subtree and the whole question for the right subtree. It's there's a set of nodes at some minimum which the connection to all the other nodes from those nodes is minimal. Let's not even go there yet. Let's just say like we just want to know like what the depth is what the depth is for any of these nodes, right? What's the furthest node? And not even what is the furthest node, but what's the value of the the length of the path of the furthest node for all of the nodes in one of these subgraphs, and vice versa, for the other subgraphs. Like I just don't know. Let's just say we found the answer. Found the answer for all the nodes. We know the furthest paths for all the nodes. Right, it's just some number, the length of the furthest path. Okay, now clearly when we connect to the root, do any of those change? Not necessarily, right? It's only the paths where the longest path includes that node that connects to the root node, right? So if the longest path we know of doesn't connect to that root node, it's only going to affect. Oh no! Oh, I gotta really think about this problem. Oh. All right, I'm gonna put the headset down for a bit. It's gonna sound kind of crazy, but I want to say it's something like it's the answer to this question has got to be the node with the largest number of immediate children, and then possibly the answer could also include, one of the immediate children, something like that. Yeah. So I want to say you could actually solve this in linear time. By just finding the node with the largest number of children. And it could possibly even be, and then you just check all of the children of that node. And it could be a whole bunch of, I mean, maybe do it in n log n time, where you sort the nodes by the number of children they have, and then you take, all of the nodes of the largest number of children. Or even no, not n log n. It's really just the largest, right? So it's all of the nodes that have the largest number, and then possibly all of their children. I want to say that's probably it. That's like the answer. Which should be, you should be able to do this in linear time then. No, never mind. That doesn't work. No, never mind. I don't think it's linear. Never mind. Okay, I gotta think about it some more. Hopefully this microphone's still connected. You know, I'm thinking, this seems to me to be a lot like the other question a while back, where we had like A knows B, and like the celebrity question, you know, A knows B, but B doesn't know A, something like that, where you're basically, I guess you're using some tricks to kind of work your way through a matrix, and through a matrix of values, because so basically what the answer I gave was too slow. I had the same problem last time on that question too. My answer was too slow, or yeah, not efficient enough. This answer is pretty much, you could build a matrix, right, of sort of like, you know, indices 0 to n minus 1 on one side, indices 0 to n minus 1 on the other side, a 2D matrix, left side, right side, or the left side and the top side. And you could say, okay, this matrix is going to be the size of the path from node to node. Obviously, node to itself, the path is 0, and then, you know, let's just say for a moment we were able to fill this matrix in time proportional to the output, which is basically the matrix is O of n squared, so it takes O of n squared time. Now, mind you, that's too much time, because we just wrote an algorithm that's roughly O of n squared time, and it was too slow. So, but suppose you did that. Excuse me. And then what you could do is you could then process that by taking at each node and just scrolling across to find the maximum from left to right of all the paths for each index. And then what you want is basically to find the minimum of all those maximums, and not only just the minimum, but all of the indices that yield that minimum, right? So there's possibly more than one index that gives you that minimum, and you just want to collect all of those indices, or the minimal value, indices corresponding to the minimal values. So that's pretty interesting. However, what I'm guessing is it's something like, you probably want to do something similar to what we did for that other problem, where you want to do this, I guess, in like linear time. And the way you would do it is, as you're building the size of the paths between nodes, you're eliminating, possibly eliminating different nodes as the possible routes. So basically, if A connects to B, then B connects to C, B is a better route than A or C, basically. And so you would eliminate A and C. Something like that. That's kind of where I'm going with this. That's not necessarily true, though. Like, I don't know. There's some kind of a rule that we gotta have. Yeah, there's a path from A to B to C. I don't know, man. Excuse me. I don't know how to do this exactly. I don't exactly know. It's challenging. We'll just say it's challenging. Really gotta think about it. Really gotta think about it. Let me think about it some more. Maybe I'll come up with something. Okay, I think I got it. I think I got it. Ah, wow, it's really unusual kind of a problem. Also, let me wipe my nose. This is definitely an unusual problem. Very kind of a unique solution, at least very different from how I would typically solve a problem, I guess. Excuse me, allow me to explain. So, what I think we're going to do is we're going to create a vector. Oh, just smacked my foot against the wall. Oh, stubbed my toe. Oh, my poor toe. Oh, ow. I didn't mean to do that. Oh, oh, my poor toe. I don't like hurting myself, you know. I feel feel bad for my body as if it's not my own body. As if I just smacked someone else's toe. Oh, poor thing. I didn't mean to do that. Ouch. All right. Oh, that really hurt. Gotta clip my toenails. Ow. Ow. Oh. Hopefully my foot is okay after that. Anyway, so this is what I think. Okay, this is what I think the solution to this problem, or one approach. We know I want to do a process of elimination and do it by induction. So we know that every leaf node is not going to be, in other words, every node that only connects to one other node, unless you only have two nodes. If you only have two nodes and an edge between them, if you only have two nodes, you just return those two nodes, right? They're done. I want to say two things, actually. Firstly, that this process of elimination, well, okay, I'll just describe the algorithm, right? And then I think I'll explain why I think it's correct. So you eliminate all of the nodes that only connect to one node, right? In other words, the leaf nodes, the nodes that only connect to one node. Eliminate all of those. And not just eliminate them, but also remove them from the graph altogether. So now you have a subgraph that doesn't contain those elements, right? Because any solution that you get on the subgraph, it's not going to include any of those other nodes, and any of those solutions that they're only going to those other nodes are only going to those nodes won't change the solution, right? Like, because those are leaf nodes, whatever solution you get, those nodes only, I guess, whatever the root nodes. I want to say something like whatever the root node is. That's I guess the thing I'm kind of struggling with is, I think the right answer, my intuition is saying, basically remove the leaf nodes and update all the nodes. Like how many. Remove all the leaf nodes and update the nodes with their new, I guess, edge sets, however, with a new number of how many edges they're connected to, and then remove all of the nodes that are leaf nodes after that, right? So now you have a new subgraph, and now remove the leaf nodes of that subgraph, and then you get yet another subgraph, and obviously update all of those, however many edges are connected to each of those nodes, and repeat that until you're left with either one node or two nodes. And that's got to be the answer, is the one node or the two nodes. That's got to be the root. Something like this, an algorithm something like this. And I think it's because the number of edges in the tree is exactly linear, it's O of n, you're going to be basically you're removing edges until you get to one node. You're removing n edges, and it's going to be n or n minus 1 edges. So if it's a linear algorithm, it's O of n time and it's got to be done correct in a way that's kind of clever, such that you so it's just done in a way that's clever, such that you don't do more than O of n work, and I'll describe that. But yeah, basically just remove nodes and edges until you get down to 1 or 2 nodes, and the nodes and edges you're going to remove each time are going to be exactly the leaf nodes. Now, why do I think this is correct? That's the key. So I'm fairly certain that I could come up with an algorithm that works to do that, to achieve that. However, the problem is, and I'm fairly certain I could do it in linear time. The problem, though, is how do I prove that it's correct? Well, okay, I guess what I could say is, let's suppose this invariant, that if we remove all the leaf nodes on the subgraph, whatever the answer is, that subgraph, it's going to be the same answer regardless of whether or not we have those leaf nodes included. That's what I want to say, is that if you have an answer and you added a bunch of leaf nodes, right? So let's say you had, I guess the proof would be that if you had a graph that had an optimal root, right? And you added a bunch of nodes, leaf nodes, to that graph, would it change the answer? Well, none of those leaf nodes could be the answer. However, it could be that it could change the answer somewhat, couldn't it? It could, maybe. Let me just think. How could it change the answer? Well, yeah, maybe they could. I don't know. I don't think I don't know if that's the right way to go about it. Maybe it's the other way around. Maybe it's removing nodes couldn't change the answer. Is that true? Whatever the answer is. I don't want to say adding nodes can't change the answer, because I don't think that's true, but removing nodes won't change the answer, whatever it was on the subgraph that, yeah. Well, removing them from consideration definitely won't change the answer, because those cannot possibly be the answer. And now the solution with regard to this subgraph, I want to say those leaf nodes now, the quote-unquote new leaf nodes, those can't be the answer either, because whatever node they're connected to, right? Since all the nodes are connected to each other, whatever node that those are connected to, those are better roots than, those are necessarily better roots than these quote-unquote new leaf nodes. So yeah, that's really it. It's yeah, we know that at each step, when we remove these nodes, that the internal node, direct internal node, must be a better root than any of those possible nodes. So we can definitely remove all those. But then once those have been removed, yet again, the next internal node, the next layer of internal nodes, again represent better roots than any of the ones that you removed. So at each step, you can confidently eliminate these nodes. Now, naturally, you end up at a point where you only have you either remove all of the edges, right? Because every node has an edge to something, and you either remove all of the edges, in which case you only have one node left, or the one edge that's left is connected to one other node, and the two nodes are connected to each other, and they're connected by a single edge. In which case, you can't say that one is better than the other because they're not connected to anything else, right? So in that case, that's sort of the base case. So yeah, so a couple things. One, that proves that there's only two possible routes, optimal routes, we'll say, or there's only one or two optimal routes. And the other thing is that we can do this in linear time. I think that the reasoning is correct. I think that reasoning is correct. It's definitely a really, really unusual algorithm. Like this is like not at all related to your. Excuse me, my shirt came out of my pants, so I want to just put that back in. Tuck my shirt in. This is not at all like what do you call it? This is not at all like any kind of searching algorithm, right? Or like it's very atypical kind of a question with regard to graphs. Because most of the time, if you see a graph question, it's almost like 95% of the time or 90% of the time or whatever, it's going to be a graph searching related question, something related to searching the graphs. But in this case, it's actually an edge deletion, edge editing algorithm, which is really unusual. Like they exist, but they're kind of rare. So this is a really interesting question. I'm glad we came across it because it's definitely stretching my knowledge here. I want to charge the headset here, but hopefully that makes sense what I was just describing. So we're going to write an algorithm now to do that. But I don't think I would have thought of this on the spot. If I saw this question, if I saw this question really in any setting, not just an algorithm question setting, but just any setting at all, I probably would have had the same issue or issues where I just wouldn't have thought of the answer, You see that? There's only one or two. I believe that's probably always the case. So pretty interesting that we were too slow. So let's do this. So the way this is going to work is we basically want to collect the. It's not going to be the children. We're going to say number of children. We'll call it n children or child count. And basically, we want to know two things: child count and also the parent. Yeah, it's going to be something like yeah, we want really like two things. We want let's do child count and children, and this is actually going to be an unordered set. Not really sure how I want to do this exactly. Still kind of thinking about that too. So we definitely want to like get all the children, right? So for auto p in edges, int a equals p of 0, int b is p of 1, and we want to say children of a dot insert b and children of b dot insert a, and then we want to say similarly for int I equals 0. Yeah, well, I equals 1 to, it's actually going to be the other way around. It's going to be for int I equals 0, I is less than n, plus I, we're going to say child count of, it's going to be the other way around. It's going to be children of I, it's going to be child count of children of I dot size push back I, if that makes sense. Tabulate the or keep track of the nodes with a particular child size, particular number of children. See, this is not, yeah, this is so awkward. I don't actually know. Let me do it this way. Let me go back. Let me back up. I'm probably gonna need this this edge set. But let me just think here. This may not be necessary. How are we going to do this mechanically speaking? Like, how are we actually going to find all of the edges that have one child? Find all of the edges that have one child. Find all the nodes that have one child, and then remove them from consideration and do this efficiently. So what I was thinking was something like a frequency map of, but the problem with frequency maps are probably like, I want to do this efficiently. Well, I think both of these are going to be unordered sets. Hash sets, really. Hash sets, basically. So you have children and child count. And the way I want to do it is like each node has a set of children, and then we're also going to keep track of which nodes have a certain number of children. If that makes sense. So there's these two hash sets. So here we have keep track of the child set. Keep track of the nodes that have a particular size, have a particular number of children. So we have a child count, and we have the children themselves. So we're going to insert. We're not going to push back. We're going to insert into the hash set for each node. Find the child, how many number of children that it has, and then we're gonna update that child count. We're gonna insert that node into that child count. So now we're gonna say for each we're gonna do auto x in child count of 1, right? For each node in child count of 1, we're going to remove that from consideration entirely. So what does that consist of? Well, first off, that child has one child right there. That node has one child, and you're going to remove the link between these two nodes, right? So child is going to be children of X, and it really should just be just one of these, right? So begin, right? That's just the only one there in the set, and you're going to remove that. Erase child, remove that child. You're also going to go to this child count set. There's a couple things that are going to happen. Using the word child so many times gives me a headache. You're going to remove it for each of these, you're going to remove it from the set. You're actually going to have a oh, this is so confusing. The problem is that we're actually going to have a new child count set of 1. Okay, we'll just say new set. We'll just say new set. Right, we'll do it that way. Okay. And then we're going to say child count of 1 equals new set. Right? The problem is that we want to erase. We are going to erase everything in this set. So we don't need to erase this child count set. It's going to get erased here when we update this new set. We're going to say from children of X, we're going to erase the child. Right. And then we're going to update by the way, we have to handle the edge case when the n is 2. Basically, we'll get to that in a second, but we'll leave that out for now. We'll just handle when only 2, 1 or we'll get to that in a second. So have this new set child count int child children of x dot begin children of x dot erase this child, and then now we want to go to children of child dot erase x, and now we say child count of we're going to say child count of this child, or excuse me, we're about to decrement this, so we have to remove it from one set and put it into the other set. That's kind of the thing, the amount. So child count of this particular child dot size erase child, and then once we do this, perform this measure, then we're going to insert this child node back. So yeah, that's why it's really confusing. But we basically get the child, and we say get the child, or let's just do y. Instead of using child, it's so confusing. Let's do y. All right. Okay. So for each x in the set of children that have a count of 1, we're going to get the first value, which is basically the parent. It's actually the parent. Really, it's parent. And then we want to know the number of children for the parent, for the children's set of the parent, that size. We're about to erase the parent from that set, and then we're going to erase from the from this child x, or from this node, from this node that only has one connection. We're going to erase the parent. We're going to erase that connection, and for the parent node, we're going to erase the connection to this node, and then we're going to add back this parent. Right now, this should have one less. It should have one less child. We're going to insert this parent back to the into the set of the child count to count this node, and we're going to recurse. We're going to have this int. We're going to do it this way, and this new set is. Now the tricky thing is see, we're removing the parent. We are removing the parent. Here's the problem. This could be, yeah, so this is what we want to do. Children parent size, erase parent. This is necessarily not in this set here. We're going to say it's actually new set dot insert, and we'll do it this way. We'll say if so int new size. We gotta do it this way. If new size is equal to 1, new set dot insert parent. Otherwise, Okay, this is the tricky thing we have to do mechanically. We don't want to be modifying this set while we are iterating through it. That's the tricky thing. And then basically we just want we'll have a count which equals n, and we'll just do while count is greater than or equal to 2 or greater than 2. And we do this. We decrement the count each time. And what we should be left with is just something like this. Something like this should be. I don't know what this will do, but nice runtime error, sweet. Let's test it on just this one here. Nice, nice. Oh, because the right answer. Okay. So it's probably this thing that's giving me an issue. I don't know. Yeah, it's definitely that. What is this 1 0? Why does that give me a problem? Oh, there's no children. That's why. What do you? Oh, just edge case. Okay. Excuse me. Oh, I'm sorry. Oh, really? Oh. Okay. Sure. Really? Seems a little weird. I don't know, there's probably a way to handle this too. But let's see if we could find. Actually, no, we know that this isn't going to be a thing, right? By the inputs they give us. Yeah. Where was the one that we failed on before? Hey, there we go. All right, how do we do? Let's give it a shot. Let's give it a shot. Hey, got there. Sweet. Okay. Yeah. That would have taken me forever, man. I don't know. That's very like. And we got there, but how long did we took 2 hours to figure that out? Oh boy. Oh boy, no kidding. No kidding. So pretty much, I mean, we got there, but wow. Whew. That's such a strange algorithm to me. It's so weird. I'm gonna just go with it. I'm gonna leave it. I'm not gonna look at the discussion. I mean, the discussion probably would be good, but this is like, yep. The basic algorithm is really simple. You just remove all of the leaf, eliminate all of the leaf nodes, iteratively from consideration, and then how I ended up coding that is pretty wonky. Maybe we should look at the discussion. I kind of don't want to, you know. But I probably should. Yeah, I probably should. It's just. It is pretty wonky what we ended up doing here. I don't know if I would have been able to do this without doing it this way. Like I think I don't know. There's probably a better way to do this. I'm afraid to. Like there's like a few comments to make. One, this is a pretty unusual graph algorithm. Like this is like a very unusual graph algorithm. It's like very specific. I don't know if I would have been able to come up with this in an interview, like on the spot. I don't think I even would have been able to code it, much less come up with it. Having seen it before, I probably could, but it's very unique. And then I guess we could look at the discussion to find out. Like we probably should. Dynamic programming, longest path, O of n time, O of n space, 2 O of n solutions, BFS, short clean solution with explanation, 99% TC. It's pretty much a BFS top sort. Remove leaves, Python solution, except the BFS. Super clean, iteratively deleting leaves. Most voted post. BFS. I didn't get the BFS, man. I didn't get that. Alright, let's do, let's just do the C++ ones. It was a BFS solution, huh? Delete leaves layer by layer until reach the root. First find all the leaves, then remove them. Removing some nodes will become new leaves. Continue removing them. Eventually there's only 1 or 2 nodes left. If there's only 1 node left, it's the root. If there are 2 nodes left, either of them could be a possible root. Each node is removed at once, so of n, pointing out any mistakes. Number of nodes is v, number of edges is e, space complexity, restoring the whole tree. Time complexity is we gradually remove all the neighboring information. Point out if a tree, O of n. I really don't need all of this. I don't know how I feel about this. Oh, that's interesting. Oh, I like this. I like this. I should do it this way. I think this is better. Yeah, I think this is better. Although this is not quite right. Wait a second. How come this works? If you decrement the neighbor, how come he doesn't have to modify this adjacency list? That's my question. How come that doesn't need to be modified? Because he's going to check all the neighbor. Like, I think this is less efficient, more concise. Yeah, there's a degree for each node. No, see, this is not as efficient, right? This is kind of a problem. These are not as efficient as they could be. Yeah, these are not as efficient as they could be. If you're doing right, if you're looping through all of the neighbors every time, or if you're looping through, because this will loop through neighbors that you've already deleted. Now, I don't think it'll give you that much more overhead, but it is considerable overhead, I believe. It really should just be one neighbor every time. Huh. Interesting. I should have used a queue. Let me try that. I'll come back to that. Let me rewrite mine with a queue. Let me try that. Whoops. Adjacency set. We'll do it this way. Right. I don't actually need to do that. So. So we'll say we have a queue, right? So we have a queue. So we'll say standard queue events queue. We're going to say for int I equals 0. So then n I adjacency set of I dot size equals 1 q dot push. So we're going to say while and q q dot not empty. We're going to parent, so we'll say int leaf. It's going to q dot front, q dot pop, parent equals adjacency. It's the adjacency set of the leaf dot begin dereferenced, right? And we're going to remove from the adjacency set of the parent, erase the leaf, and we really don't need to do anything else, I think. I don't even think we need to, I don't even think we need to, well, yeah, we could decrement the count. And then if the adjacency set of the parent, so we can actually auto reference just parent set so we don't have to continuously keep re-referencing that. If the parent set dot size is equal to 1, then we can q dot push the parent. And I think that's all we need, really. Something like this, maybe. I think this is a little bit cleaner, this approach. We probably don't even need to mess around with these edge cases either. What does this do? answer. Nice. 3-1. Oh. Uh-oh. Just thinking here. What? Wait a second. There is a situation where I think I got myself confused. Managed to confuse myself. Oh, okay. Let's think for a moment. This is kind of wrong, I think. You got to do a level order to do this properly, by the way. Yeah. Few things. There's a standard queue, new queue. Forgot about that. This actually has to be done properly. What is this? What's happening here? So we don't need to bother erasing the leaf set, the parent from the leaf set, because we're never going to touch the leaf set again. What's going wrong here? There is something to be said here about this. Oh, that was it. Okay, interesting. Neat. What about this edge case? Did we handle this properly now? I think we do. I think this is handled properly now, yeah. Right, let's give it a shot, see how we do. Hey, okay. It's a little bit better. I think I prefer this way. Yeah, it's kind of just is what it is, I guess. I think this is like really succinct, really concise. Excuse me, really clear. Not as good as it could be though. It could be fast, even faster, and use even less memory. Probably there's a way to do this without keeping this. Trying to think if there's a way to there's probably a way to actually, because there's only 2 numbers, it's probably a nifty kind of thing we can do. Let me see something here. Let's do this. This is kind of neat. I want to try something kind of unusual. Oh yeah, the count here. Alright, let's try something kind of unusual. Do some bitwise operations. Some bitwise shenanigans. So if there's only 2 nodes left, then you can say helper is going to be, I guess the parent we'll use. Right? And what should happen now is we say actually we could do it this way. Count is less than 2. We'll just return ret or return ret helper XOR helper ret, something like this. Oh, really? I didn't know that. Okay. I did this wrong anyway. Should be the helper that we return. How about that? What does that give us? Hey, it's the right answer. Whoa, worked for everything. No kidding. Let's give it a shot. Oh, that's right. That's a little faster. A little less memory. A little less memory, a little bit faster. I like that. I like that. I don't need that anymore. Can do a little bit of bit manipulation because we know it's only going to be two numbers, two values. And it even handles the case when there's only one node, it's just 0, right? So it even handles that properly, which is kind of neat. Clever, huh? Clever, huh? Yeah, basically you can, you basically end up duplicating when you add it, you XOR, you put it in, and then when you XOR, it removes it. So you have sort of this bitwise manipulation, which is kind of neat. Instead of sort of having a visited set, I guess. Not a visited set, but yeah, trying to, you're removing all the values except for 1 or 2. And then you can just, once you hit 2, you can just pick one of the parents and boom, you got both values. I feel so smart. I feel so smart with that approach. Neat. Pretty neat. All right. That's probably it for this problem. Really interesting problem, interesting approach. Just thinking, yeah, layer by layer deleting leaves. That's fine. I think this does the same thing. Yeah. It's technically a BFS, but not really. Okay, so they call it BFS, but it's not really. Alright, you just did the same thing everybody else did. Okay. It's technically BFS, but it's not. I wouldn't call it a BFS, man, because it's. Yeah, this is a level order traversal, just removing the leaf nodes, but it's not. It's not that simple, right? Like a breadth first search, usually a level order traversal or a breadth first search, it's like, I don't know. I guess I could take it back then. I guess I should have recognized this as a level order traversal or a breadth first search level order traversal. Like, I want to say something like you wouldn't necessarily see that easily from a problem like this. Like, this is pretty. I like this problem a lot. This is a really interesting problem, but it's kind of hard to see it. It's kind of hard to see it for what it is. Also appreciate that I got the opportunity to use some bitwise manipulation in there to reduce our memory footprint a bit. I don't know if this is, this may not be the best way to do this, but it's one approach. I like it, I think it's pretty good. But apparently there's a way to do it that's even faster and then uses less memory, which, I don't know. I don't know. maybe you would use the edge set somehow, something like that. Maybe to get a count. I don't know. I don't know. Yeah, I'm not really sure. I'm not really sure. There's probably a way to do it. Let me go. So thank you all for watching. I appreciate it. I'll talk to you soon. Have a good rest of your night. I am going to take a break and then probably take another look at another problem before I go to bed. Probably do one more. I want to eat some food too. My diet has been terrible lately. I've been like not so comfortable with the food that I've been eating, so I haven't been eating as much as I should. I'm also like not lifting as much because I'm like really sore when I lift because I haven't been exercising for a long time because I've been messing around with a bunch of different things. So it just kind of gives me a headache when I think about food, just because things are like I can't easily get. I need to look up fibrous foods that are not asparagus, because the problem with asparagus is it's too stringy for my teeth, and the strings get in between my teeth, and then I feel like my teeth are my gums are gonna get infected because the food basically rots in between my teeth, which is absolutely disgusting. And I bought some dental floss, but one, it's a real pain in the neck getting the asparagus out of my teeth, and then it's also I don't think it really works that well. Like every time I use it, I'm like bleeding or something. I'm kind of like I don't really think that's like a good long-term solution to be flossing every time I eat. So I'm not super excited about eating my meals, but like I need to eat. So I'm in this weird flux kind of a position right now where I got to figure things out with regard to food. But anyway, that's neither here nor there. That's unrelated. But yeah, I'll probably take a break, kind of lay down for a bit, look at another problem. Yeah, man, I don't know. This I don't know. It's a good question. It's a hard problem, interesting problem, challenging problem. I definitely would have bombed it in an interview. Overall, not too crazy, not too hard. It's just, I guess, seeing it, realizing was the hardest part. Realizing that you know what you want to do to solve it, to remove each layer of leaf nodes one at a time. That's a very subtle, nuanced, clever kind of a solution, I suppose. Obviously once you realize it doesn't seem that clever and nuanced, but before you realize it, it's like, yeah, man, how the heck are you supposed to figure this out? Yeah, so interesting. I'll have to keep that in mind for graph-related problems, that there's a good chance you'll see a level, like if it's not obvious what to do, a level order traversal is probably what you're going to need to do, because those are kind of less obvious, less common, less intuitive. Yeah, and just kind of ponder what it might be. Okay, all right. Thank you all for watching. Take care. Talk to you soon.